All right, can everyone hear me out there in virtual land? Drop a comment in chat if you can hear me. All right. That'd be wild if you typed in no. Try to figure out what that means. At any rate, name of this course is Web Database Integration. And we've introduced you to the web part of it, right? How we're going to do this particular implementation of server-side code is using ASP.NET Core, using Razor Pages. Right? Razor Pages consist of a CSS document, which is like an HTML document, except we can pull things from a model and put on that page. It's sort of like a form that you can fill out, or not you fill out, but your model fills it out by doing calculations or retrieving from a database or whatever. So we're going to see, we've seen that already. Now we're going to get into the database part, and we're going to access the database part in sort of a different way than conventionally was done with applications. And if you've done database access before, maybe you've done it a different way, but the way we're going to do it is kind of cool, and it's sort of the newer way. And we'll talk about that probably next week. Depending on how the lecture goes today, it's possible that we'll go over it today, but more than likely we'll save that until next week. What we're going to do today is, by and large, review database terms to make sure that you understand the basics of database design, because that really serves to be the foundation of a whole app. And this is true regardless of the kind of app it is. It could be a desktop app, it could be a web app, it could be a mobile app. It doesn't really matter. The database serves to be the foundation. And if the foundation is strong, you can build upon it, and you can change it, and you can add stuff to the database, change things in the database, and it'll be okay. If, however, the database was built and it's not very solid, then any future changes that you have are going to be problematic. All right? So much of software development is us writing code and doing things in such a way that will make future changes easier. All right? We do that because we know that all software is going to change, right? So it's not a matter of if an application is going to change, it's a matter of how is it going to change. And therefore, we want to introduce as much flexibility as we can into our application development. And that sort of starts at the database, all right? So we're going to go over a few terms here that sort of are the basic terms. And I'm not sure if I want to draw that. Well, we'll do both. I'll have my drawing open, and I will also have a Word document open that I can type into. Typically what we talk about when we talk about databases, the term database is short for the word, or short for the term relational database. There are other kinds of databases, but most conventional databases that we consider today are relational databases. And that's important. In the past, data was stored using files. All right, and they were called flat files often. And they could have been delimited files or fixed length files or whatever. But the problem with files is that the data between different files was not easily connected. Therefore, you had to write fairly intricate code to connect one thing with another thing. For example, if you had a customer file and a sales file, or you had customers that, you sold products to. So it's a third thing. If you had a product file, a sales file, and a customer file. You would have to actually write the code to connect those if you wanted to see all the things that a particular customer bought, for example. Or you'd introduce duplicate data into the system. So if it was too hard to connect the customer and the item and the sales, what you'd do is you'd duplicate information about the customer in the sales file, duplicate information about the items in the sales file. And that led to all sorts of problems when you were updating it. Think of this as being like Excel worksheets. We had our customer file. And we had a customer number, a name, an address, a city, state, who our primary contact was, who our secondary contact was, and so on. If we then developed our item file, maybe it would have item number 123 is, let's say these are grocery stores. So item number 123 is a case of bottled water. Item number 456 is, and the price of the case of the bottled water is, what would be 24 in a case, say $36. And 6-pack of seltzer. Maybe that is $8, and so on. When we got around to having our sales file, we'd have to do one of two things. We'd have our invoice number, let's say. We'd either have to put in the customer number, the item number, the date of the sale, do something like this. Say I bought a case of seltzer water and a 6-pack of seltzer on my order. So 111 is the order number or the invoice number. Either one. Let's call it the order number. Now, we'd have to do one of two things. We'd have to either write the code that goes back and connects the customer with the order, or we'd take a shortcut and would store customer details with every order. This is what was often done. We would put data redundantly in related tables. And what's the problem with this? The problem with this is we can make mistakes. We could, for example, spell the name Zeller's Inc. wrong. Get the address wrong if we stored the address. So there would be duplicated data between files. Guess you could get away without that, but then you'd have to write a lot of code to match things up. Relational databases solve this problem by doing two things. You remove redundant data, redundant or duplicated data. And two, we store the relationships between things. This is a benefit of relational databases. Now, again, this doesn't happen by magic. This happens if you follow a good process to design a database and to follow some rules in designing the database. These rules are called normalization rules to create a normalized database. If you do that, you will have effectively removed all the redundant data, and you will also store the relationships between things. Right. Let's go over some terms here. Table. Sometimes you call it an entity. Sometimes it depends on who you talk to. Sometimes it depends on what part of the process you're in. For example, when you're designing a database, before you've created it, a lot of times you'll talk about entities because they're abstract. When you actually create the database, you have a concrete table there. So you might refer to them as tables. And the table contains all the data about one kind of thing, right? So for example, if we were designing a database for a school, there might be a professor table or entity. That should contain all the professors and all the pieces of information about the professors. So that would be an example. A column, sometimes called a field or an attribute, is one piece of data. About the entity. So in the professor table, there would be a column for professor ID or faculty ID. There would be a faculty ID is probably a better way to say it. I'm going to change this to faculty. Because some faculty are not professors. And this naming is important. It's important that you get the right names for these things because it can be very misleading and confusing otherwise. So when you're designing a database, make sure you pay close attention to the terminology that people within the organization have. So a column or field is one piece of data about the entity. I sort of skipped one. A row or a record goes here too. Are all the fields or all the columns about one member of the entity? So the faculty table would be a table or an entity. A column would be an attribute, would be one piece of data about the entity. Maybe the faculty ID number. Okay. Maybe the first name. Maybe the last name. And so on. These would all be fields. If you take all the fields for one person, one member of the faculty ID is 1, 2, 3, let's say. First name is Mike. Last name is Zellers. That's called either a row or a record. Again, depending on who you're talking to and when you're talking to. I introduce these extra names not to confuse you, but just to help you clarify if you ever come across in a reading or if you're researching something online and you hear someone talking about a row or a record. There's actually more formal terms than these in database terms, but those usually aren't used a lot. Let me Google those real quick. Relations, tuples, and attribute. The relation is the table. Tuple is what we've called a row. And then the attribute is one field. It's good to know different terms, just again, in case you're talking to different people or you're reading something online or whatever. Most people in the business world would probably use table, row, and attribute, or table, row, and column. Now, we can define constraints for a bunch of things. That's one thing that's easier to do in a relational database than it is in a file. If I have an Excel file like this, I'm storing something, this has to be a number. Guess what? I can put anything in there. Databases contain information about the data. It contains what's called metadata. There's not just the data itself that's stored, information about the data and its relationship is stored in a relational database. Some of these constraints include the data type. Is this field a integer? Is this field a decimal? Is this field a string? Is this field a Boolean? Is this field a date? Along with other possibilities. Those are some of the most common ones, though. So there's data type constraints that you can put on it. So I could define when I define the faculty ID column that it has to be an integer. No one has a faculty number of 123.456, right? Everyone's faculty ID number is an integer. People's names are going to be strings. They're not going to be dates or something like that. The nice thing is by putting these rules in the database, you enforce them regardless of what application is accessing the data. It's important to put as many restrictions as possible in your database to get the best data possible. Some of those constraints are the data type. Hey, you make sure if it's supposed to be a date, that it gets a date. And guess what? I don't have to write code to do that. I don't have to write code to ensure that the data is a date when it's supposed to be a date or an integer. I define that in the database, and no one can get past the database management system to get bad data in. It's a big advantage of relational databases. In the past, I spent a lot of time talking with the past, I know, but I think it's important to understand where some of these systems came from to really understand the advantages of them. In the past, you had a bunch of these files sitting out here, and you had a bunch of programs that read and wrote to these files. Things like validation of the data had to exist in every program that accessed it, that accessor wrote to it. Now, our applications go through database management system. And that's what accesses the database, rather than each application directly. Therefore, if I try to give the database management system bad data, it knows the rules for the data. A well-designed database will have as many rules defined as are appropriate. Many rules as possible, as many constraints possible. That will limit the the amount of bad data that you get. And therefore, the stuff coming out of the system has a greater degree of accuracy. One of the oldest acronyms in the computer business is garbage in, garbage out. By implementing constraints in the database, you help ensure that you don't put garbage in the database, which means that you're not going to get garbage out of the database. Another one is required. This is a yes or no question. Is this column required? Does everyone have to have a value for that column? Well, again, in the old days, if you wrote an application that used files, every program that accessed the file system would have to make sure that if a field was required, that it was filled in. Here you can define that constraint in the database itself, say whether a field is required or not. And if you try to write data to the database and something that is required is missing, the database will give you an error and you won't be able to get past it. DBMS is a gatekeeper. It's not going to let bad data go into the database. Another kind of constraint, which the first two are kind of obvious, I would say. The next constraint, which is maybe a little less obvious, is what's called referential integrity. And this gets to the idea of a foreign key. That's a constraint that we want to build into our database. Now, it sounds a little bit funny, like constraints. You know, I don't want constraints. I want to be free to do whatever I want to do. No, that's not true with databases. You want to build in as many constraints as possible because that will have a greater guarantee of the data being good and the data being accurate. And if it's wrong, it's easily correctable. You can put these constraints in and still have problems, right? You could say something's a date and still enter the date wrong that you have to go back and correct, but it should be something that's easy to correct. Before we talk about referential integrity and foreign keys, we should talk about primary keys. All MDs have what's called a primary key. All tables have a primary key. Now there might be some, well, I don't even want to talk about possible exceptions. Just consider that a rule. Every entity is going to have a primary key. And a primary key uniquely identifies, there's two requirements for, or two of the requirements for a primary key is it must uniquely identify. Uniquely means one, only one. So if I have a faculty ID of 123, no one else in the system can have a faculty ID of 123. Otherwise, it's not unique. The other rule about primary keys is they are required. If I designate a field or combination of fields, then all of those fields I define are required. In other words, this is my faculty ID. I'm going to put an asterisk to indicate it's a primary key. Put other stuff here. My faculty ID is 123, first name, last name. I couldn't have Nate Neeland in here unless he had a faculty ID. So this would not be acceptable to have my database table look like this. That's a violation. That's a violation of the constraint because one of the rows does not have a value for it. This would also be a violation of the rules. have two with the same ID. Now, sometimes it's hard to figure out a key. For some things it's obvious. Like faculty, it would be, your employee number, whatever your employee ID number was. In the student table would be your student ID number. If we had a table that contained all the buildings on campus here, it would likely be the building code, the business being the BU building, the ILOF being the IL building, the University Partnership office being the UP building, College Center CC. That's unique, right? There aren't two CC buildings. If I tell someone to go to CC 107, there's only one CC building. There's no ambiguity between two different CC buildings. Therefore, it's possible for, it's not possible to, send someone to the wrong place because there's another building that has CC as its code. Now, what about email? Could that be a primary key? The answer to that is yes, it could be. Given that every employee here has an email address and they're all unique, right? Even if there was another M. Zellers that was employed here, they'd give them a different email address. They'd give them mzellers1@lawrencecc.edu or something like that. You might notice that on your own student email. I forget how those are constructed, but a lot of them have numbers, or some of them have numbers. If there was someone that had similar to your name before, you'll get a number at the end of your email address. Now, can I make both these a primary key? No. I can't make this a primary key because that violates the rule that primary keys ought to be minimal. What do I mean by minimal? I mean this. Primary key by itself could be, or the faculty ID by itself could be the primary key. The email by itself could be the primary key. But there's no need to make both of them together to be the primary key. No need to make both of them together because the primary key could be smaller. If I got rid of the email address and just did the faculty ID, that would be good enough. Right? I made the email and got rid of the faculty ID as part of the primary key. That would be enough. So you need the smallest sufficient set of fields. Now, why would I pick IDs instead of email address? I don't want to send them an email. Simply because numbers are stored more efficiently than characters. Therefore, that's going to take up less space within the database. If there's ever something that you can't think of an ID for, you can always use a generated number. Generated value as an ID. For example, we have the rank of a professor. We could have a rank ID of 1. Meaning instructor. 2 being assistant professor. 3 being associate professor, 4 being full professor, 5 being professor emeritus, and maybe 6 being adjunct. Could we use a description as a primary key? Yeah, but that gets to be long. Again, numbers are easier to store than letters. So better to store just a simple number here than to store the description. So, on to the relationships between these and the foreign keys. Every professor only has one rank. They're one of these 6 statuses. I don't know what everyone's rank is, so I'll just make stuff up. I'm an associate professor. Elon hasn't been here this long. I'll say he's an assistant. And Harms is probably also an associate professor. Notice I'm storing the primary key of this other table. Storing the value of the primary key of the rank table as a column in the professor table. That is what a foreign key is. That's why we had to talk about primary key before we talk about foreign key. A primary key is where we store, or a foreign key is where we store the primary key of one table as the attribute in another. And this creates a relationship. Between the two. There's a relationship between ranks and faculty. Each faculty has a rank. So this is a required field. Each faculty has one value for rank. But each rank can have more than one faculty member for that rank. So Zellers only has one rank, but associate professor has multiple professors that have that rank. That's what's known as a one-to-many relationship. And in the case of a one-to-many relationship, that is implemented by having the one side point to the many side. And that would be drawn like this in a diagram. This is what's known as an entity relationship diagram. And to talk about the relationship, you have to look at it going both directions. One faculty has only one rank, but a given rank can have multiple faculty members. A one-to-many relationship. And that's implemented by a foreign key. So the many side, the faculty, contains a rank ID to point to the one rank that that faculty member holds. Here's the thing about a foreign key. And again, you don't have to write code to do this. That's a great part of using a relational database. I can't put in a number 7 for harms. If we do that in a plain old file, it would let me do that, unless I had really extensive code to validate it. With the relational database, because the database management system is a gatekeeper, it will not allow, if there's a foreign key defined between two tables, it will not allow me to have a faculty member that doesn't have a valid rank ID. I just can't do it. I can't force it in there. I would have to assign them a valid faculty rank. Now there's 3 kinds of relationships. But those 3 relationships sort of get mutated into one kind of relationship. And I'll explain to you what I mean by that. All right. I mean that there is this kind of relationship, which is a one-to-many relationship. There's a one-to-one relationship that you can draw like this. Might be the example. An example of this might be that a baseball team and a manager. Each baseball team only has one manager. Each person as a manager only manages one team. It's a one-to-one relationship. There's also what's known as a many-to-many relationship. An example of that might be the relationship between students courses. One student can take multiple courses. An individual course can only be held or can contain multiple students. So that's a many-to-many relationship. Now the good news is this. We're going to change that student relationship to a pair of one-to-many relationships. So one-to-one relationships are pretty rare. There are times when you'll see them, and there are some specialized cases that you probably went over in database class, but for our purposes, we're just enough to say that they're rare. So that cuts one of them out of the way. That leaves us with one-to-many and many-to-many. Well, one-to-many are very common, and so are many-to-many. But many-to-many relationships get broken down into 2 one-to-many relationships. So really, you just have to know how to do one-to-many relationships. What will be an example of a one-to-many or many-to-many relationship? Maybe the relationship between committee and professor. We have a lot of committees here on campus. And they contain, several faculty members. And each faculty member can be on more than one committee. And each committee can have more than one faculty member. So maybe the one is general education. Maybe another committee is about salary. Another committee can be about, let's say, reducing the cost of textbooks. Now, I can't put that as an attribute in the faculty table because I might belong to 2 committees. And according to the normalization rules, which I hope you all have somewhat of an understanding of, I can't have repeated fields, so I couldn't have committee 1 and committee 2. So I can't put committee 1 if I was in general education and reducing textbook costs. Likewise, since multiple faculty can be on one committee, I can't put a faculty ID over here. So what I have instead is I have a faculty committee intersecting table that contains a faculty member and the committee or committees that they belong to. So this taken together would be the primary key. And each of these would be foreign keys over to the appropriate table. So there's a one-to-many relationship between committee and faculty committee rows, and there's a one-to-many over here. So that's how we've taken the many-to-many relationship and broke it down. Right? An exercise on Canvas that I hope would be largely reviewed for you. We'll talk about this next time. Because here's an old example, because I have 2003 and 4. Wow. Flash. Wow, that's old. Try to take this one file, which is like a spreadsheet of data, and figure out how many tables you would come up with. Remembering that there shouldn't be any duplicated data. So I should not have in the computer table the building name, because then each computer would have a building name attribute, and that would be redundant data. Data would be in the building table. Can't be any repeated fields, so no application 1, 2, and 3, so on. We'll probably look at this as the first thing in next Tuesday when we go over this. Then I have to decide what we're going to do. We might talk more about this, or we might talk about how we get this database structure into our ASP.NET Core app so we can do stuff with it and we can integrate with the database. Are there any questions? All right, that's all I have for today. Have a good weekend, and we'll talk to you on next Tuesday. If at all you have any questions at all, please bring them to my attention.